Hello everyone, I'm very honored to be able to share my research findings with you at this important international conference. Before I begin my presentation, please allow me to briefly introduce myself. I'm Zhu Shanshan from the School of Computer Science and Technology at Anhui University, currently a graduate student. The work I'm presenting today is titled COTuner approach that joint organization of resource configuration and software parameters for recurring stream jobs on the cloud. My presentation will be divided into 4 parts as following. Firstly, I will introduce the introduction of our work, mainly include background knowledge and motivation. First, due to consideration of operational efficiency and cost effectiveness, the deployment of big data pipelines on the cloud platforms has become commonplace. And since the batch of streaming jobs are usually recurred in a certain period, the selection of resource configurations for each software in pipeline plays a vital role in cost reductions. Besides, each software also has a number of performance-related parameters which can be tuned to further reduce the resource cost. Thus, appropriate resource configuration and software parameters for recurring jobs can significantly reduce the resource cost. In addition, there is some strong dependency between different framework configurations, and there are also some strong dependency between cloud configurations and performance configurations. Thus, it is necessary to joint organization the configuration parameters and the software parameters. Thus, in our work, we focus on joint organization of resource configurations and the software parameters for the recurring stream job on the cloud. However, addressing the corresponding joint organization problem is not easy, and there are some challenges. Firstly, the potential combination of resource configurations and software parameters create a high-dimensional solution space. Second, the relationship between system performance with resource configurations and software parameters is difficult to model and usually have to be treated as a black box. Third, the cost of the experimental evaluations is also not negligible. Thus, to address those problems, we design a method called COTuner. We're using BO dropout algorithms to address the high-dimensional black box problems, and we introduce a pseudo-pointer mechanism and hyperparameter-aware mechanisms, which can enhance the convergence speed. Another part 2 is about the COTuner detailed design. This is the system overview of the COTuner. As shown in the figure, developers need to specify the software performance configuration space, the cloud configuration space, and the observation times constraint. and the COTuner will work in the form of iteration. First, the algorithm generates a new configuration based on the current observed dataset, and which is then returned to the controller. According to the new configuration, the controller will request the cloud service and return to the information of the generated virtual machine class. Then we'll start all the virtual machines and do some initialization operation. Next, the framework is installed automatically and is installed automatically in the deployment streaming process systems, and the software configuration is updated to the system. After that, the head bench will automatically start, and we use the load generator to generate different streaming jobs and then submit the streaming jobs to the streaming system. After that, the performance metrics are plotted along with the configuration parameter values, and the new observation samples will be returned to the controller, which updates it to the observation dataset. Finally, the observation dataset is returned to the algorithms. When the number of the observer samples reach the specified constraint, COTuner stops running and recommends the optimal configuration to developer. And this is a detailed description of COTuner algorithms. The most important part is the build dropout algorithms and the pseudo pointer mechanism. For each iteration, COTuner will randomly select d-dimensional parameters to optimization. Then, COTuner will adopt all the hyperparameters using a hyperparameter-aware mechanisms. After that, it will generate a pseudo-pointer set based on the current date, and then the COTuner will recompute the surrogate model based on the older dataset. Next, it will apply the Bayes optimization to solve these optimization problems, and finally, it will use a certain string to fill in the rest of the configuration parameters. Besides, we also design a score function to evaluate the quality of the configuration. The function expression is as shown in the figure, and there are also some hyperparameter descriptions as shown in the table. And in order to verify the effectiveness of COTuner, we conduct a corresponding experiment on a local distributor class. The experimental settings were as follows. It includes experimental environment, the full baselines, and the full benchmark, and another experimental settings. First experiment is to evaluate the effectiveness and the efficiency of COTuner. We compared COTuner with full baselines. Specifically, we utilize each approach to auto-tune the configuration parameters for the word count, stream task, and the head bench. The table shows the optimal cloud resource management cost. the number of iteration times, and the total observation cost found by COTuner, and for other baselines. The experimental results show that the optimal cloud resource management cost of COTuner is lower than other four baselines, which can further reduce the cloud resource management cost of the streaming task word count by at least 33%. And to evaluate the adaptability of COTuner to different streaming jobs, we employ three streaming benchmark tasks to evaluate COTuner's effectiveness. As shown in the figure, for different streaming tasks such as word count, representation, and fixed windows, COTuner achieve cost reduction of at least 33%, 25%, and over 33% respectively. From the experimental results, we can find, due to its dropped-out strategy, COTuner incurs low total observation cost compared to all baselines. And to provide a more in-depth analysis of COTuner, we conduct a series of population experiments that describe the improvement and advantage of COTuner. In this experiment, we used COTuner without hyperparameter-aware mechanisms and joint conf to tune the configuration parameter or word count in the bench. Through the result, we can find that through its hyperparameter-aware mechanisms, COTuner can break out a local optimal during the optimization process, facilitating the search for global optimals. And through its hyperparameter-aware mechanisms, we can find COTuner is more suitable for solving a high-dimensional configuration space optimization problem in the streaming process system. And in addition, we carried out additional experiments to showcase the effectiveness of COTuner in the context of Spark streaming with Kafka message queues. As shown in the figure, we can find that COTuner is also can find the optimal configuration with lowest cost, having good performance in both effectiveness and cost on the Spark. Finally, in conclusion, we propose a COTuner, a joint observation approach on resource configuration and system parameters for the recurring stream jobs on the cloud. In COTuner, there are mainly three parts most important. Firstly, we use BO dropout algorithms to address the high-dimensional black box optimization problems. And we introduce the pseudo-point mechanisms to enhance the convergence speed by adding pseudo-points in each iteration. And finally, we leverage the hyperparameter-aware mechanisms to adapt COTuner's hyperparameters to the varying workloads. That's all my presentations. Thanks for your listening.